Okay, now we're going to talk about how to model two types of constraints in your reservoir simulator. I'm going to resort to this matrix form which I showed you before, right? Because it's easy to explain and make it very concrete. And so, obviously, this is your transmissibility matrix for all of the grid blocks in the domain. This is your vector of primary variables. So for multiple phases, it's going to be pressure in the oil phase and saturations. This is your diagonal matrix corresponding to the accumulation terms. So it's also your accumulation matrix. Of course, time step size, delta T, change in the primary variables from current time step, or better still, from previous time step to current time step at n+1. And we have the Q is the flow rate vector. So if you want to have a constant flow rate in a well, or better still, constant flow rate in a cell, right? Because in your reservoir simulation domain, what you have is grid blocks. So if you want to have constant flow rate in a well, which is in a cell, you need to be able to go to the corresponding row and column where the cell is located, and then in the equation for that cell, provide the constant flow rate. So in all the other cells that don't have wells, flow rate is 0. So if we had a transmissibility matrix, it's just a toy case that was 3 by 3. Solution variable is, say, let's just assume it's pressure in grid blocks 1, 2, 3. And then we have a diagonal matrix that has zeros everywhere except in the diagonal, and we multiply that by this vector of dx dt. Basically, that's what this vector is. So what we need to do is to add the flow rate. So if there is no well in all 3 cells, so we're modeling, say, flow through these cells, no well in all of them, so Q will be 0, which is why we haven't been talking about it. But if you want to produce cell 1 at a constant flow rate of 100 barrels per day, then you will go to the row or the entry corresponding to cell 1 and you put 100, and the others will be 0. So that's basically how we model constant rate. Just plug in the value for the flow rate in the row corresponding to that cell. If you have another well in cell 3 and the flow rate is 50, put 50 there. Actually, you will put minus 100 for injection. So let's assume this is simplified. Let's assume 100 is an injection. So we are injecting here at 100 barrels per day, but we are producing here at 50 barrels per day. So you will have minus 50 because, like I said, when you're producing, the sign is minus. When you're injecting, the sign is 100. So that's how you model constant rate wells. Very straightforward. Just go into the corresponding row for that cell and put in the value of the flow rate. The sign is positive if it is an injector. The sign is negative if it is a producer. How about constant bottom hole pressure? How do you model constant bottom hole pressure constraint? We don't need to write this all over again. I can take care of this first then. Okay, so for constant bottom hole pressure constraint, this is the equation, right? For actually this one. For flow rate, as a function of average grid block pressure and flowing bottom hole pressure. So we want this guy to be constant. So what do? Essentially, what we end up doing is to expand out this expression. And before we expand it out, let's look at it in terms of transmissibility. This expression for flow rate basically is transmissibility, right? When you group these two together, it's transmissibility multiplied by some pressure difference. So the way we expand it out, because transmissibility is a matrix, is to use matrix multiplications. That's why you see I just put pressure here. Why? Because if you want to do one pressure minus the other as shown here, all you need to do is to put, say, -1 here and 1 here. When you multiply by, say, P1, P2, P3, you see this will be P, it will be minus P1 plus P2. So you have essentially found the pressure difference between cell P2 and P1. So that's how we basically expand out these kinds of calculations in matrix form. So this equation can be written in matrix form as in this form. And for the pressure difference, it's important to know that because the pressure is constant, we will be subtracting out a constant value, which will be corresponding to the connectivity, the well index multiplied by mobility, multiplied by the constant PWF, which we specified. So I'm basically expanding this out, which is what is shown here. And then this will be evaluated in the code. And the only thing we need to find out is the product of this transmissibility and the pressure in that cell. And the summary of the long story is that you will have in the rows and columns corresponding to, so this is your transmissibility matrix. Let's assume we already had a T here, a T1 here, which was multiplying P1, P2, P3, right? P4. Then in one of these cells, so if it's cell 1, you will multiply it by a T, which is the well index. I'm just going to call it TW index. So that will basically be equivalent to evaluating this first part of the equation. Then you subtract out this fixed constant rate, and the simulator will automatically ensure that the pressure in the well is kept constant. So the pressure in the well will be kept constant by implementing it in that form. And that's how we model constant flowing bottom hole pressure constraints in your reservoir simulator. We look at the form of this equation, express it in matrix form, then modify the transmissibility to incorporate the connectivity index for that grid block in which the well is located. The other cells, the other rows and columns will have their corresponding transmissibilities without a modification. We're not going to talk much about multi-layer completions, but the summary is that because your well can run across multiple cells, and those cells will now need to be connected through the wells, so you will have different equations for the different well segments, and they will be coupled linearly with the equations for the grid blocks. So what we end up having is governing mass conservation equations. Then we extend out the matrix to account for the equations for the wells. So you have multiple equations for the well. So this is more complicated in the sense that the matrix actually grows bigger. because you're not only solving for the primary variables in the matrix, you will also be solving for the flow rate or the flowing bottom hole pressure, depending on what you use as the constraint. So that's basically the gist of it. And it messes up with the sparsity structure of the matrix, which is what is mentioned here. But your numerical solvers can take care of that. And the final slide here points out that even though the Weyl index, the equation for the Weyl index looks very much like that for the productivity index, they are slightly different, and they are precisely different here. This is equivalent to the reservoir boundary, basically. But here, it's equivalent to the equivalent wellbore radius, basically. RO is equivalent wellbore radius, which is approximately 0.2 delta X for cuboid, for cubic cells, basically. So that's how we find out RO in your reservoir simulator. But from production, from well test analysis, RE, which is radius at the boundary or some other form of equivalent radius, is different from this. They are not the same. So very important to take that into consideration when you're using set PI in any simulator. So make sure you don't use the wrong RE or assume the wrong RE when you're providing your productivity index as an input to your simulator. How do you know what the simulator does? You will need to check the user manual or technical reference for that simulator. And it's very important. It could change your results significantly, because as you can expect, some equivalent radius corresponding to radius at the boundary of the reservoir will be much larger than an equivalent radius which is just a fraction of the size of one grid block in the domain. So very important to take that into cognizance. And that ends up the section on well treatments, and next we'll move on to look at aquifer modeling.